Continuing on with universal gravitation here, Newton's law of universal gravitation. What happened is taking those two relationships, that the force is related to the masses and also inversely related to the r squared, to that distance, we made this formula. Well, Newton put together this formula. The force of gravity equals big G m1 m2 over r squared. So that just means mass of object 1, mass of object 2. We don't square or do anything with those numbers, they're just subscripts. This superscript up here means we square it. Okay, big G is not the same as little g. That's a huge mistake that kids often make. Big G is the gravitational constant and it's on your formula sheet, not something you're going to have to memorize. Okay. It talks a little bit about how this is an inverse square formula, which we will see in other places. And so if you ever see an inverse square formula, it's related. Okay, now we could take this formula we just found, and if we solve for big G, if we wanted to get big G all by itself, this is what that formula would look like. So just solving formulas, rearranging formulas rather, and how we're going to put numbers into the formula. Okay, the only thing he could measure Fg would be an object on Earth's surface, like you. We could calculate the force due to gravity on your body easily using Fg equals mg. And again, I want to remind you that that's F, that should be a subscript. Okay, it just didn't come through on the smartboard here. Okay. The distance from the center of Earth to your center, and I'm going to tell you that, that's 6.38 times 10 to the 6 meters. And they even had a good estimate of this in Newton's time. We need to know your mass, which would be mass 1, no problem. The last thing we need is the mass of the Earth. Now, how can we find the mass of the Earth? No one had any idea how heavy the Earth really was in Newton's time. But if we knew G, then we could calculate the mass of the Earth. But that's what we're trying to calculate here. Newton continued to look for some way to calculate this constant indirectly, but never found a way. Luckily, Henry Cavendish came in. Okay, he attached a really heavy pair of metal spheres to the end of a long metal rod. Okay, here's his spheres and the long metal rod. Hung the rod from a wire. He brought another pair of really heavy metal spheres near the spheres in the rod. He knew because they had a mass they should all pull on each other, but very weakly. To measure this weak pull, he carefully measured how much the wire was twisting, and a name for that is torque, whenever he brought the other masses nearby. This is why the device he used is called a torsion balance. After really careful, tedious tries, he found that G was 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. So this number is really 6.67 times 10 to the negative 11. Sometimes they use an E in different resources. That just means times 10 to the negative 11. Okay, sometimes on your calculator you could even have like a double E button like that. Okay, but don't use your little E button. It's just a different way of writing it depending on the resource. Okay. Because he knew the value for G, he could now calculate the mass of the Earth. So he titled this paper, Weighing the Earth. So using values that we know, we're going to determine how much the Earth weighs. No cheating, don't look it up. We're actually going to calculate it. Okay? Let's see if I can move that out of my way. Okay. So a few of the things that we know. We know that the force exerted on my body by the Earth is my weight, which we can calculate using Fg equals mg, where m is my mass. I also know that the force could be found using Newton's big universal gravitational formula, where one mass is my mass and the other one is the Earth. Let's make these two formulas equal each other. So the force of gravity, my weight, is also equal to force of gravity. So we said this is equal to m of me times g, and this is equal to that new formula, g m me m of the earth over r squared. Okay, if something is on both sides of the formula and there's just multiplication, if it's on this side and this side, we can simply cancel those out. We divide both sides by my own mass. Okay, now I'm left with G equals big G, mass of Earth, over R squared. Okay, solving for the mass of Earth, if I wanted to get mass of Earth by itself, I'd have to times both sides by R squared and divide by G. So just doing some math here. So the mass of Earth is equal to G over G, little g, over big G, R squared. Okay, we know all these values. We know G, we know R squared, and we know big G. So now we're simply putting in those values that we know. Okay, M Earth. And I'm going to get you to look this up. I'm going to get you to pause the video. G is 9.81 or 9.8, depending on which resource you're looking at. R, we were told the radius of the Earth somewhere up here. Where were we told it? There we go, 6.38 times 10 to the 6 meters. And we were also told big G, that is a constant that's on your formula sheet. So I'd like you to calculate that out. I'd like you to press pause here, and I'll share the answer I got and see how we do. Okay, hopefully press pause. When I did this, I got 5.99 times 10 to the 24 kilograms. So this is how he found out, Cavendish found out, the mass of the Earth, how he weighed the Earth.